Okay, thanks a lot. Yeah, thanks for the introduction, Gail, and thanks also for the invitation. As Gail mentioned, this is joint work with David Fraser. And it turns out that a lot of the content of this talk is actually covered quite well in other talks. So I should be able to go through the slides quite quickly, which is good because I have 35 slides to get through, which is probably too many. But let me see how I go. Okay, so we just have an observed data set where we've got n observations, and we propose some statistical model for this data, which is parameterized by theta. And we'd like to obtain some kind of approximation to the posterior distribution, which is proportional to the likelihood times the prior. But for whatever reason, the likelihood function is not tractable to compute. And so therefore, we're going to resort to likelihood-free methods. And in these methods, we make the assumption that we can generate simulations from our statistical model, and we use this in order to approximate the posterior in some way. So there's a couple of popular methods, popular likelihood-free methods in the statistical literature called ABC and BSL. And traditionally, these methods reduce the full data set down to a set of summary statistics. And the kind of idea behind that is we want to kind of overcome this cursor dimensionality problem by trying to match data sets in high dimension. And so in these methods, we don't actually target the original posterior, we target this so-called partial posterior, which is proportional to this term over here, which we might refer to as the summary statistic likelihood, and then multiplied by the prior. Now, of course, this likelihood here is also going to be intractable, but we can use ABC and BSL and model simulations in order to approximate this one in various ways. So in ABC, we approximate the summary statistic likelihood using this expression down here. So we generate M simulations according to our statistical model based on some proposed parameter theta. The row here is just some kind of distance between the observed summaries and the simulated summaries. This term over here is a kernel weighting function that's designed to give high weight to when your distance is small. And then finally, we have this epsilon, which is like a bandwidth parameter. And this is basically like a bias variance trade-off in the approximation of the likelihood. So if your epsilon gets smaller, then you reduce the bias, but then you also increase the variance. Okay, so then you have some kind of approximation to the likelihood, which you can put into some Bayesian algorithm, for example, SMC or MCMC. So here we're going to be using MCMC. And then we also have BSL. So BSL makes a multivariate normal assumption for the summary statistic likelihood. That involves a mean vector mu and a covariance matrix given by sigma. And so these are allowed to depend on our parameter of interest, but unfortunately, we don't know what the relationships are between these parameters, but we can estimate them by simulation. So again, we generate our M simulations from our statistical model. We compute the summary statistics for each of those simulations, and then we compute the sample mean and the sample covariance. And then we can plug them straight into our multivariate normal density and evaluate this one at the observed summary statistic. And then this gives us our BSL approximation to the likelihood, and we can also feed this into an MCMC algorithm. So there's also lots of extensions to BSL that were covered very well in other talks by Leah, Jacob, and also previously David. But in this talk, we're just going to be focusing on the standard BSL because we're using standard ABC, so it makes sense to compare it with standard BSL. Okay, so I guess the big question in likelihood-free methods is how do you actually choose your summary statistics? And there's many different approaches in the literature for coming up with different ways for getting the summary statistics. I guess a good place to start might be Dennis Prangle's chapter in the ABC handbook. But there's many different approaches, and from my experience, it seems like that the best summary statistics is usually going to be problem dependent. But for the examples in this particular study, we found that an indirect inference approach seems to work pretty well. So we're just kind of using this as a generic approach for these particular examples. So what we do with indirect inference is we propose some alternative auxiliary model that does actually have a tractable likelihood function, and it's parameterized by phi. And then we go ahead and we fit this auxiliary model to the observed data to get this estimate of the auxiliary parameter. We form the score function of the auxiliary model. And then for the observed summary statistic, we evaluate that score function at this parameter estimate. And if this estimate is the MLE, then the score is theoretically going to be equal to 0. And then for the simulated summary statistics, we pass the simulated data set into that same score function using the same parameter estimate for that auxiliary model. And for the examples in this work, we used a Gaussian mixture model as the auxiliary model. Now, so this is all very well and good, but there are some issues with using summary statistics. So the first thing is, well, how do you actually choose the summary statistics in practice? And as I mentioned before, the results that you get with likelihood-free methods can be very sensitive to the choice of the summary statistics. And I guess the second issue is that the summary statistics are generally not going to be sufficient statistics. So they are in some examples, but for most examples, they're not sufficient, and therefore you're going to lose some information. So your partial posterior is not going to be the same as the true posterior. In the last few years or so, there's been some different works which have focused on coming up with smarter ways to compare the full data sets without having to reduce down to a set of summary statistics. And the basic idea is, can we compare these data sets by using empirical distributions? So now there's actually been quite a few approaches that have been proposed in the literature. And in a previous talk yesterday, Hien spoke about these very nicely, so I can go through them reasonably quickly. So I'll talk about a few of them here, but I'll also just have a disclaimer that David is the real expert on these particular approaches, and he sort of wrote this part of the paper. So I think it's a bit unfair on him to try to give two talks back to back, so I'm just going to have to try to fumble my way through it. So let me see how I go. Okay, so the first one is the Wasserstein distance. So it's got this kind of fancy formula over here, but if you make these particular choices, then it essentially involves comparing these order statistics. So you obtain the order statistics for the simulated data, the order statistics for the observed data, and then you compare them in this way. So the good thing about the Wasserstein is it's very quick to compute, and it should perform well if the quantiles of the model simulations are sensitive to the parameter. We found that it may not perform very well if you have heavy-tailed data. So if we go back to the way that this looks, if we've got heavy-tailed data, then the Wasserstein distance may be dominated by those outliers, and so this is why it may not perform particularly well in that case. And it may also not perform particularly well for time series data, and this is because if you look at the time series from a univariate point of view, then the quantiles of that data may not be very sensitive to the parameter. So for time series data, maybe what you might like to do is combine the Wasserstein distance with some other summary statistics that tell us about the features of the dependent structure in the time series. The next one is the energy distance. So an approximation for this one is given by this expression down here. So a potential issue with this approach is that it requires the existence of the moments. And so if we think about, for example, a stable distribution, this assumption is going to be violated. And this is a little bit concerning because stable distributions are often used as examples for likelihood-free inference. So for this particular reason, because it may not be suitable for stable-like distributions, it may not perform also very well when we have heavy-tailed data, and so it may not be robust to outliers. And furthermore, if you have a look at the approximation on this previous slide, you can see that the overall computation for this is going to be order n squared. So if the data set is kind of getting large, then this could be computationally intensive. The next one is the maximum mean discrepancy. So it's actually quite similar to the previous one. The difference is that we have to choose some kind of kernel, and it seems the standard choice in the literature is a Gaussian kernel. with the standard deviation chosen in this particular way. So as I mentioned before, it's similar to the energy distance, and it turns out that the energy distance is actually a particular case of the MMD distance. And so therefore it may potentially suffer from similar problems compared to the energy distance. And furthermore, we have to choose a kernel. The next one is the Cramer von Mises distance. And the idea with this particular distance is that you compare the empirical CDFs. That's the basic idea. So what you do is you take your observed data and your simulated data, and then you order that to create this vector of observations. And then you look at the ranks within that H for the observed data, and then you look at the ranks also for the simulated data, and then you can compute this Cramer von Mises statistic using this formula here. So the good thing about the Cramer von Mises approach is that it's very fast to compute, because all you have to do is work out those ranks. And also we've found that it's quite robust to heavy tail distributions and outliers. And this is because basically the Cramer von Mises distance is comparing empirical CDFs. So if you're looking in the tail of the distribution, then the empirical CDF is going to be close to 1. And so the distance is not going to be as heavily influenced with outliers with the CVM compared to something like the Wasserstein distance, which might be dominated by those outliers. Another potential advantage is that we can use this particular method in any application where we can reliably estimate the empirical CDF. So therefore, it might be a little bit more applicable to some different applications. So for example, when we have some kind of dependent structure in the data. Some potential limitations are that we found that it doesn't necessarily perform very well when we have small samples. And we think the reason for that is that the estimate of the empirical CDF can be quite noisy. And finally, it may not perform very well on parameters that control the tail behavior. So as I mentioned before, the CVM distance isn't particularly sensitive to what's happening in the tail. So therefore, if we have parameters that are actually controlling this tail behavior, then we may not get very precise inferences for those parameters. The next one is the Kullback-Leibler Divergence. So I think most people are familiar with this divergence. So I guess the question is, well, how do you estimate this thing? And this paper used a one nearest neighbor density estimator of the KL divergence, which is given by this expression here. So this one is also useful in the sense that it's order n log n. So it's only a little bit slower compared to the Wasserstein and the Cramer von Mises. But some potential limitations is that the estimator is only applicable to continuous distribution. So it's only going to work if we have continuous data. So if we have either discrete data or a combination of discrete and continuous data, then it may not work particularly well. And finally, it generally makes the assumption that the data is IOD. So if we had time series data, for example, then it may not necessarily perform as well. Now, there's another summary statistic free approach that's not really ABC, but it's still likelihood free, but it doesn't really fit within the ABC framework. So the idea of this one is you make the assumption that the observations are independent. So you can write the likelihood function down in this way. And then what you do is you simulate a data set of size m, and you use that simulation in order to construct a kernel density estimator for this likelihood part for a particular value of the parameter. And then you just estimate the likelihood by plugging that KDE into there. So it's kind of like some kind of simulated version of the actual likelihood. So we're going to refer to this particular approach as the KDE approach. And under some pretty mild conditions for kernel density estimation, then this method is going to become exact in the limit as the m goes to infinity. So a potential limitation of this one is that the observations need to be independent. And secondly, it can be slow if the number of data points is large, because then we need to take the m to be large. and that causes the KDE to be slow. Okay, so that was kind of like a qualitative comparison of the different methods. So what we were kind of really interested in is, do these approaches, can they actually overcome the curse of dimensionality with respect to the dimension of the data? And secondly, how do they compare with each other? And then thirdly, how do they compare with summary statistic-based approaches? So we compared these methods on a few different examples. So we've got these three methods here, which were the ABC full distance approaches. We've got the KDE, which was the alternative likelihood-free approach that also uses the full data. And we also have ABC and BSL, which were the summary statistic-based approaches. So for these two ones, we use exactly the same summary statistics. So we allocate roughly the same amount of computation to each of these methods in terms of the number of model simulations. When the example is not computationally intensive, we look at the results for replicated data sets. And when the example is computationally expensive, then we just look at a couple of data sets and assess the performance visually. Okay, so here's the different examples here. So I'm not going to have time to go through all of the details of these examples. I'm just going to talk about particular features of these examples. The first one is the G and K, and I guess anyone familiar with ABC probably knows this example quite well anyway. So it's got 4 parameters, and we look at data sets of size 100 and 1,000. As you can see here, the data is quite heavy-tailed, and we've assessed the results based on 100 replicate data sets. So for this particular example, we found that the CVM seems to perform the best. The KDE and the BSL performed relatively well. We found that these particular methods performed relatively poorly. And we think that the Wasserstein and the MMD didn't perform so well in this one because it was probably impacted by the heavy-tailed nature of the data. The next example is a queuing model, which is also very popular in the likelihood-free literature. So for this one, we have 3 parameters, 50 observations. So this is a relatively small data set. And as you can see from the data, there's some skewness there, but we don't really have a heavy tail. And also we considered the log of the data. So we're considering what happens to these methods when we also include a transformation of the data. So by applying this log transformation, we've kind of removed the skewness in the data. So for this one, now the KDE performs the best. But in terms of the ABC full distance approaches, we found that the Wasserstein method, provided that you do a log transformation of the data, actually performed the best for this class of methods. So it was really kind of interesting that the log transformation of the data had such a big impact on the performance of this method. And something that was also quite interesting is that for this example, the Wasserstein massively outperformed the CVM distance, whereas in the previous example, the CVM outperformed the Wasserstein. So we think that the poor performance of the CVM is due to having a small data set. The next example is a stereological extremes example. So this one was spoken about in David Knott's talk. So this one's quite interesting because the data set consists of a mix of zeros and the rest of the data are continuous. And the model actually generates a random size for the data. So what we did was we included the number of zeros as a summary statistic and then treated the continuous data in the usual way. So, coming up with some kind of distance for the continuous component of the data. So for ABC, we had to combine the summary statistic with the distance. So we basically combined those 2 distances together to form an overall distance. And for this one, the model is much more computationally intensive. So we just considered 1 simulated data set and 1 real data set. For this model, we have 3 parameters and there's around 100 observations. So again, it's a relatively small data set. And we do have some skewness in the data, but it's not super heavy-tailed. Okay, so firstly, comparing the full data approaches, we found that so what did we find here? So we found that the CVM method doesn't perform particularly well, and the Wasserstein and the MMD do perform particularly well. So we think again that the CVM doesn't perform so well.
5 minutes.
Yeah, no problem, thanks. So we think that the CVM distance doesn't perform so well because we have a relatively small data set. And given that the Wasserstein distance is faster to compute compared to the MMD, we take the Wasserstein as the winner out of this one, and we take that winner and we compare it to the summary statistic-based approaches. So as we can see, it's also very competitive with the summary statistic-based approaches. So maybe the DSL gives a slightly sharper inference, but there's a very similar performance there. And so that was for the simulated data, and for the real data, we qualitatively got the same results. And now moving on to the final example, which is the toad example. So this is the one that Jacob spoke about in his talk. So this one's sort of similar to the stereological extremes one in the sense that we've got, again, a mix of zeros and continuous data. And also the model itself generates a random size of the data. So this one's a little bit more tricky though, because we have that for 4 time lags. And so this means to obtain the overall ABC distance, we need to do some kind of weighted average of 8 distances. So for this one, we have 3 parameters. And as you can see from the figure here, the data is quite heavy-tailed. For the simulated data, there's about 1,000 continuous observations. And for the real data, there's about 100 continuous observations. So for the simulated data, the data set size is quite large. So we found that the MMD was too computationally intensive. So we didn't consider this one. So for this one, we found that the Wasserstein didn't perform that well. And we think that this is because of the heavy tail nature of the data. But if you consider the log transformation of the data, then the Wasserstein performs just as well as the CVM. Now, taking the CVM method as the winner out of this one and comparing it with the summary statistic-based approaches, we found that it's also quite competitive. But again, it seems that the BSL may be giving a slightly sharper inference. And we also got qualitatively similar results for the real data. So that was, I think I've got about a minute left. So let me try to summarize the key results. So we found that the ABC with the full distance can be competitive with ABC with summary statistics. But the performance of the full distance approach is really problem dependent. So it really depends on what kind of features you have in the data as to which of these methods is going to sort of perform the best. So we have kind of a general impression that if you put in enough effort to finding really good summary statistics, then you can probably do better with the summary statistic-based approach. But who knows how long it's going to take for someone to find some really good summary statistics. Something that we also found, which maybe hasn't really been discussed much in the literature, is that these full data approaches, the performance can be very sensitive to transformations of the data. And for future work, we would like to look at the performance of these methods when the model is misspecified. In pretty much all of these examples, we're just dealing with univariate data. So we'd like to know how these full distance methods go for multivariate data. And finally, in this work, we focused on parameter estimation. We'd like to see how these methods perform compared to summary statistic-based approaches in the problem of model choice. Okay, so that's it from me. The work that I spoke about here is in this archive paper, and here's a few other references there. Thanks very much.
Thanks, Chris. It's from the floor of the screen. Yeah. Do you want to maximize the people?
Chris, can you start sharing your screen, mate, so we can see everybody?
Oh, yeah, sure, yeah.
Thanks, mate. Cool. There we go.
Right, so some questions for Chris. here. We're talking about who chatting away then. Here.
Oh,
Chatting
good
away.
question.
Oh, yeah. Where's that one?
Christian.
Oh, Christian, yeah.
I'll read it. So Christian Chris has asked about the impact of dimension. Do you mean of the parameters, Christian? Of theta or of y? Y.
Yeah, so that's a really interesting question. So in all of these examples, the dimension of y it's just univariate data. And so I guess these distances are mostly applicable to the one-dimensional situation. I think there's been some literature on trying to extend these things to higher dimensions, but I don't think that this sort of question has been explored much in a likelihood-free setting yet. So it would be really interesting to have a look at the multivariate extensions to these distances and see how well they perform. And so, yeah, this is something that we'd really like to explore in future work.
Can I ask a question? Oh, Florence, yes. Florence, yes.
Yes, thanks. So maybe it's a very a naive question, but for the full distance approaches, would it make sense to combine different distances? Like you showed that they had different characteristics. So would it make sense to combine two of them or three of them to capture like both the tail and the central part or whatever?
Mm. Yeah, Florence, actually, that's a really interesting question and something that we didn't explore in the paper. So I think that could be beneficial to do that. So not even just combining different distances, different full distance functions, but also combining distance functions with summary statistics. So there's no reason why you can't combine some kind of overall ABC distance, which involves that full data distance and also some summary statistics in there. So it could very well be that for particular examples, you might get better results by combining those things together.
Okay, so maybe it would be computationally evident.
Yeah, I think it might be difficult. So how do you weight the different distance functions? So I think that that might be difficult to address, but yeah, I think it's a good idea.
Okay, thank you. Thanks for the talk. Very nice.
May I just comment something?
Yes.
Massimiliano here.
Yes.
No, just related to the last point, how you combine them. Well, one possibility might be to have some sort of pilot study if you are dealing with the simulated data to see the impact on the different distances. I mean, you fix your true parameters. You run your simulated data, you perform your ABC or your approach, and you see actually what's the variability of the distance over the different repetition, and then you have an impact of actually how good is the measure, how good is the distance in terms of capturing the randomness that is intrinsic in that model. And once you have done the pilot on a set of simulated data, you can have those weights for the real data set or for whatever machinery you have to do that.
Yeah.
We did something similar in a paper where actually we were having data that were not IAG, but were coming from some statistical model. And we used initially the old data set, and then we mapped to invariant density and invariant spectral density because we have non-IID data. And then we were combining these two measures. We were considering actually as a distance, we were considering nothing else than the integrated absolute errors between the two estimated these measures, and then running this pilot study to have a weight for summing them up.
Yeah, I think that's a really nice suggestion. Yeah, thanks a lot. And actually, there's a comment that just came through the chat about using other distances, and so I think this is a really good point. Yeah, so I think any kind of literature related to goodness of fit can be carried over to to ABC. So I think, yeah, find another distance that's used in goodness of fit tests and apply to ABC and write a paper.
Can I just say that this, even though I don't, David might not agree with me here, but this whole idea of the sensitivity to the transformation of the data really reminds me of the original Francois and Bloom paper that talked about the importance of transforming the summary statistics in a particular way to get an improved performance. So it's really got that sort of same flavour, hasn't it? Anyway, that's just a comment. All right, well, let's keep on track and let's give Chris another clap for a really good. Okay, so now we have Olivier